Okay, it's almost time, or this time actually. I stop sharing. So if you start sharing your screen, Virginie.
I will start. Does it work?
Yep.
Yeah.
Okay. So let's see. I have to set the live stream. Okay, the final talk of today will be by Virginie Wiktor. She is from Cugla in the Netherlands, a company that makes all kind of admixtures for concrete. And before she joined there, she's head of research there. Before she went to that company, she was at TU Delft as a postdoc, and she was one of the people that started with the self-healing concrete with bacteria. So she contributed very greatly to that development. So that's where we know her from, and she's also now in the SmartThings project as one of the partners. So but she will tell us all about what you can add to concrete to improve the properties. Virginie, the floor is yours.
Thanks, Eric. Hi, everybody. First, I would like to say I'm really glad to take part in this training school. And also, if it's online, I think it's a really nice alternative. And so far, I think very well organized. It works very well. So also a big thank to Eric and his team, because it's really nice and interesting. It has been a quite intensive week and day. So I hope you still have some energy for our last talk. And I will try to keep it a bit more dynamic. So today I will talk about admixture. And first I would like to start, if it works. I try to change slides. Okay, do you see the first slide? Yes, good. I would like to start with a citation from Neville. And he said that the ingredients of good concrete are very simple. If we look, we have water, cement, sand, aggregate, mineral additions, and chemical admixtures. And I think this is what we've seen today. These are the basic ingredients. But if you look about bad concrete, yeah, essentially they are the same ingredients. So what makes a difference between a good and a bad concrete? And I think that has been, really well explained in a different presentation today. The difference how to make good concrete and bad concrete with same ingredients is the know-how of making concrete and how you understand how these different materials interact between each other. If I think about ingredients, I'm always thinking about cooking. And what you could see is with admixture, you can compare admixture for concrete, what spices are for cooking. If you look, in both cases, you have to select your main ingredients. So you will have a recipe if you cook, but you will have a mixed design if you are making concrete. And then the choice of the spices you will use is very important for the final results of your dish. If you have the wrong spices, then you have a drama. And it's the same, exactly the same for chemical admixture. You can do a lot with them, but you have to choose them very carefully. It's not like one admixture fits all. You need to choose them for really the purpose you want to. And now I think a lot of you have seen cooking shows on TV, and you see sometimes you have the same high quality ingredients, but you also have to know how to use this ingredient, because if you don't mix it properly or not with a good proportion, you have something that doesn't work. While if you really use it properly, you have a fantastic dish. So that was small introduction, like to see, okay, what are admixture, because they are very small amounts, but they can have really a big effect on your concrete. And today, what I would like to talk about, I will present a bit what is Cugla, what we are doing, and how can we support you in the research also. Then an overview of our chemical admixtures. And then I want to spend a bit of time on cement hydration, because this is important, because this will be one of the main interaction between your admixture and the cement hydration to the final property of your concrete. And then I want to go more into details over how do admixture work. And there are a broad range of different types of admixture. So I will start with dispersing admixture. And I think by then we will be around 1 hour talk already. So I think will be time for a small coffee break. And then to continue with retarding, accelerating, and air entraining admixture. And that would be more the theoretical part. And then I want to say a few words to say, okay, it's nice, you have different type of admixture, but how do you select admixture? And how can you formulate admixture and see, do I have the admixture that have the right effect for my concrete? And I hope there will be some time so for questions, but also to have some discussion. How could you use admixture in your project? And yeah, so then we can have a discussion about it. So first, if we look about Cugla, we are located in the Netherlands in Breda, and we have 2 plant facilities, 1 plant for the admixture and 1 plant for production of mortars. And next to it, we also have a research and development center. And if you look, so here are the Netherlands. The production capacity of Cugla is here in Breda, but we also have one sister company in Belgium that is Demula, and it is in Larne. And if I'm right, this is close to Ghent. And we also have one office in Germany, in Grono, and this is at the border with Germany and Netherlands, and this is for the German market. So if you look about the admixture plant and what we do there, so what we do, we develop tailor-made admixture system. So what does it mean? We not only formulate admixture for concrete, but we also provide technical support. Because it's not, I mentioned before, and I hope it will be clear in the presentation, you don't have one admixture fit all, but the admixture needs to be really well to match the purpose of your concrete. And if in time you also have change in your material and different cement, or if you use slags that have different properties, it means you have to adjust the formulation of your dosage of your admixture, and this is something we can also provide. About the admixture we have, so we have a wide range of different admixture we can formulate from. Next to this, we also have mortar plants. So we produce special-based mortar, and there you can think about windmill grouts or faceting grouts. Faceting grouts are grouts that reach 30 megapascal in 2 hours of cold mortars. And Michael asked also the question how you should do in the winter. If you have special mortar, then they will have a strength development in low temperatures, the same as a 20 degree. And of course, for this special type of mortar, we use a lot different type of admixtures. But next to it, I said we have production plants, so it means we need to have a quality control, everything that comes in, but also everything that we produce. So we do this control in the lab. But we also do a lot of R&D, research and development, and we have 2 labs, one analytical lab, and here you can think about X-ray diffraction, X-ray fluorescence of PSA, and to characterize your material, your cement, or your mineral additions. And this is maybe more familiar to you. This is a concrete lab, where you can do the mortar mechanical testing, but we also do concrete. If we look about chemical admixture, so they are regulated by standard, and in Europe, then you will have to deal with the European norm 934, and especially part 2, that is concrete for admixture. And outside Europe, there are also standard, and this is more the American standard. They are classification in the same type of admixture, but the classification varies a little bit. In the American standard, and they are classified by type A, B, C, or D. According to the European standard, so the admixture are chemical, and what is important, so they are added to concrete, mortar, or grout, cementitious material, and they are added during the mixing process. They can be added at different stages, but it's always during the mixing process. and they are added at less than 5% by mass of cement. So this is what in the norm, but typically in practice, we add them 0.3 to 2%, and this is by mass of a cement. Why do we use admixture? We use them to modify the properties in a fresh or hardened state of the concrete. And you can find them in a powder form. So this is what we use also when we produce mortar. But we also have water-based solution. Water-based solution, which means that the admixture you will have active contents, but you will also have some water in it. And it was mentioned also this morning that in your mix design, you have to take into account the water that is contained in your admixture for when you calculate how much water you need to put inside your concrete. So there are water-soluble chemicals, especially if you talk about the powder form. You can find single components, but most often the admixture nowadays, they are a blend of different type of admixture. So then you can really have a broad range of properties of your admixture. So this is a classification. There are like more than 10 types of admixture. I won't go through all of them, but today these are the admixture I will talk about. For some more into details than the other, and why this choice is because now these are the mainly used admixture. The other are of course used, but not as much as the orange type of admixture. And due of the time, I say, okay, I won't go through everything, but I cannot cover everything today in a presentation. So please, if you have questions later, do not hesitate to take contact with us. We can have also online extra meeting of, if circumstance can, we can also meet for real. So if we look about development of admixture, yeah, admixture are not new. Already from the Romans and before, they were using urine as a retarder for concrete and blood as air entraining agents. But when we really started with chemical admixture in the 30s, the naphthalene was for the first time patented. But at that time, so naphthalene, the technology was there, but it was only on a patent and not commercially available. So it was not translated into an application into the concrete industry. So later in the 30s is where you see the apparition of lignosulfonate for plasticizer and also more carboxylic acid salts. And this is also for retarders and some waterproofers. And in the 40s then was found that you can have air entraining agents, and this could increase the resistance against frost. What is interesting to see, so you have the first regulation for admixture was around in the 60s, but also in Europe. Okay, in Europe you also have some the norms that are come where it specifies the water to cement ratio you should use in your concrete, which strengths you need to have. So the property of the concrete were more regulated. And then the use of admixture also was more important. At the same time, you see that you have development of super plasticizer with the naphthalene that was at that time available commercially, and the melamine. And later on in the 90s is where the PCE, the super plasticizer, these are the late generation of super plasticizer. I will say more about this one because the possibilities, what you can do with PCE is almost, I won't say infinite, but you can do much more. What is interesting to see is that you go to high performance concrete, self-compacting concrete, ultra high performance concrete, and this is only possible if you also have developments in a chemistry of your admixture. So they go in line. If we go what we have now with a lot of pressure to reduce the carbon footprint of concrete and cement industry, so we want to lower the clinker content. So you ask for most challenging mix design, and if you still want to fit within the strength class, the environmental class, and you need to have also specific types of admixture. And you see that, in the late years, there have been new type of structure for PCE, and then you can have more demanding mix design. For the future, yeah, we are dealing now in this project with self-healing concrete. And if you see a new type of concrete, ask also new type of admixture, of a different way to formulate admixture. So you can think maybe, okay, this is a situation now, but we can think of another way how we can combine this admixture differently. As Willy Westrate has mentioned yesterday, maybe you can think of new type of admixture. Maybe your healing agents can be used as an admixture. So then you see that in a development of admixture, you have new development, and that goes in line with the development of self-healing concrete also. Is it for now clear? Yeah, still everybody on board?
Yes.
Yes, good.
Yes.
Good. So I will continue with some cement hydration. Maybe it's more familiar for some of you, but I guess not everybody. So just to look about how it works synthetically. This is a cement particle, and you have three main phases. You have your silicates, and the silicate you have your tricalcium silicate and dicalcium silicate. You have your aluminate, tricalcium aluminate and your ferrite, and there are some sulfates that is added to your clinker. Now what is very important is your tricalcium aluminate, your tricalcium silicate, and your sulfate, because these are the main phases that will, in the first place, react. As this will happen, so it's chemical reaction, and these are exothermic reactions. So if you follow the heat flow that you have here on the vertical axis, with the time of hydration, you see if you have a peak, it means you have a chemical hydration. And when you have a flat line, yeah, then you have decrease in chemical reaction. So for cement hydration, you have basically 5 steps. And the first one, you see you have a very high and a sharp peak. And this is from the moment when you have your cement, your binder, and your aggregates in contact with water. You have immediate dissolution of a different ionic species. And you have an initial hydration of your tricalcium silicate, the C3As, and your C3A. What will happen? If you have your aluminate, it will react with your gypsum, and then you will form etchangite. So this is really fast. And then at the same time, you will start to have dissolution of your tricalcium silicate to form a CSH gel and some portlandite. But the CSH gel that you see here, it's really a jelly structure and not yet in the structure that you will have a CSH in a concrete. But what does it mean? So you will have some hydrates that are immediately formed, and it will cover the surface of your cement particles. So which means it will also be like a barrier that you cannot have further a reaction. And this is what you see in step 2. It's called the dormant period. And this period is characterized by reduced chemical activity. So what happens during this period? You will still have a dissolution of your silicate, but this comes very slow, and then you will accumulate in your solution some calcium ion and some silicate ion. And so, oops. And when this concentration of this ion will reach a certain value, a supersaturation level, then you have enough to nucleate, and then they will grow. So, and when they will grow, then you say, okay, then the chemical reaction will speed up again. And this is when you go to step 3. So step 3, as you can see, you have a very steep increase in heat flow. And that means, so you have a lot of nucleation, it will grow. And you have, at that time, massive precipitation of your CSH, so hydration product from your silicate, and also your portlandite. And because you form a lot of products, it triggers more dissolution from your C3S to form even more. So it's also when you see the setting and the hardening of your cement paste. So at the beginning, when it starts to speed up, it's the initial set. And when it reaches an equilibrium is your final set. And then you can see that you have at the top of this curve. And it means that the CSH that precipitates in a needle-like will cover your surface of your cement particle, and then it will decrease again the speed of reaction. So it's what you see in part 4. So part 4 is a deceleration period. And that means because you have a layer of hydrates, you have a slower diffusion of the ions through the layer of hydrates. What happens, I said in step 1, you have hydration of C3A to have some ettringites. So it's immediately, but then it stops. And here you will see a renewed hydration of your C3A because you still have some sulfate present and some C3A. So this is what you see with a peak, with a shoulder. And this reaction will take place as long as you have sulfate. And when you don't have sulfate anymore, then you cannot have ettringite formation anymore. Then you have step 5, and step 5 is more a quiet fast, quite heat release. And this is because you have formed already a lot of hydrates. So if you want still from the inside of your cement particles and to dissolve and to still form some hydrate, it needs much more time to reach the place to precipitate. I mentioned before that you don't have a sulfite anymore, but if you still have some C3A inside your system, this can react with your ettringite, and then you can form some monosulfoaluminate. And this you see because you have a small bump in your curve. That's also where you have your C2S and a ferrite that will hydrate. So they are there on your in your cement particles initially, but in the first hours, they won't do much or not contribute a lot to your cement hydration. So that's why when you look about the hydration and about how admixture we will use, we are mainly focused on the C3S and the C3A content because this is what triggers your workability, what affects your workability and your setting of your concrete. So now how do admixtures work? There are different ways that you can work, but I've just shown the hydration of the cement, and then you can say, yeah, if I want to increase the setting time or decrease, then I have to play with a chemical reaction. So an admixture can accelerate or retard one of the phase. So you can see with the dormant period, you can shorten this dormant period, or you can extend it. And you can also see the purple line. This is the hardening phase. And then you can say, okay, the hardening rate can be faster or slower. And then you will have the strength development that will go in line faster or slower. So this is one way where admixture can work. But another way is you have your cement particles, and it's also, you have some charges over there, and you can have your admixtures that can adsorb on the surface of your cement particles, which means that if you have two particles and you have admixture around it, then you will create some space between these particles, so you will have better dispersion. And this is typically what we get of the mechanisms, what happen with plasticizing and superplasticizing admixture. Then you can also find a way to affect the rheology of your water. And this you will use this type of admixture if you want to have an increase in the plastic viscosity, or if you want to create more cohesion in your concrete mix. Another way that you can use admixture for, if you affect the surface tension of your water, then you can stabilize the air bubbles that you have in your concrete, and that's typically how we will use air entraining admixture. And finally, you can have an admixture that initially won't do much with your hydration process of your cement, but then you will bring specific chemicals inside the composition of your concrete that can add added value later, such as corrosion inhibitor, or if you can think about water repellents, and it's like a hydrophobic material. So, oops, sorry about that. Up. So this is a classification I've shown before, and I will first start with these two first categories because they are one family. They both are dispersing admixture, but depending on the type, they have a bit different requirements. What do? They can increase the flow of the slump, depending what you are looking for, without affecting the water content. But they can also permit a reduction of the water for a given concrete mix. And in some cases, and especially for the super plasticizers, they can do both. So you will have an increase in workability, and at the same time, you will have reduction of your water content. If we here to summarize, so this will be your reference concrete. And then if you want really to target increase of workability, then you will keep, you mix the same, you will just add some dispersing admixture, so your strength won't be much affected, but you will have an increase inside your workability. Now you can think, okay, I want to have higher strength, but I can work with a constant workability, which means you will have your dispersing admixture, you will reduce your water content, and this will translate with a higher strength development in your mix. And then you can combine the two effects. So you have a dispersing admixture, you can reduce your water, and then you can also reduce your cement content. And this is really interesting if you look about the cost, but more important is also if you look about the environmental effect of the concrete and cement on the environment. How do they work? So this is a picture you've seen a few slides ago. So silicate, aluminate, and sulfate, this is still your cement, but you can see it a bit differently. You can see your silicate more a negatively charged area. And your aluminate, you can see it more as positively charged area. So what will happen when you put this into water, positive, negative lot each other, so they will attract each other. And what will happen, you will trap some water, they will agglomerate, and then you have some water that will be trapped. And this water is not available for your workability. So sometimes also on the workplace, you say, oh, I don't have enough workability, so you just add a bit of water. It's fine, you have your workability, but then it goes to cost of your strength. And this is not something you want. So ideally in such situation, what you want, you don't want to add more water, but you want to have workability. So you need something that goes in between your grain and that will separate them. So they will disperse them, and then your water will be again available for the workability. And this is how dispersing admixture work. If I first look for plasticizing admixture, so they are also classified depending on the water reduction they bring. And for water reducing or plasticizing admixture, you should think about more than 5% water reduction and less than 12%. Dosage is also very low, 0.1 to 0.4% of cement. And if you look at the dosage, and sometimes if you compare different products, you should always be careful what is the concentration of the solution, because not all admixture have the same concentration. And some are 40% and some are 20%, which means that the end dosage can be different. Here are the requirements, still according to the norm. And you see that the first requirement is relating to the water reduction. And that, as just mentioned, more than 5% to a control mix. But you also have some requirements relating to your strength. So you can reduce water, but you should. It also means that your 7 days and 28 day strength is higher, 110% higher than your control mix. And this is a requirement that you will find for all admixture. Besides air entraining agents, is the air content in your fresh concrete. It can increase a bit, but no more than 2% compared to a control mix. And it was mentioned also by Michael that the air content inside your concrete can really negatively impact it. And I think as a rule of thumb, you can consider that for every % of extra air you have in your concrete mix, you have a loss in strength from 4 to 5%. So that's why also you can have admixture, but you should also be careful that you don't have more than 2% extra air. About the composition, so they are based on lignosulfonates. Here I show a chemical structure. I won't go more about the structure, but what is good to know, they are a natural product. from the wood industry, so which means also that the quality and purity of this admixture is also varying in time. It means also that the performance of the admixture can be varying. What is for the lignosulfonate also good to take into account, so is that in a solid content, in a spent liquor, you have about 25% that is sugar. And sugar can cause retardation in your concrete. So if you look, you can use lignosulfonate, but depending on your dosage, you should be careful over does it bring retardation to your concrete mix or not. So that's why is here a mention. You can have, if you have a dosage range in a higher range, then you can have a retardation. And it's also not the best admixture to use by low temperature. And to consider if you have also on the high range of your dosage and you say, yeah, still my dispersion is not high enough, you should take into account that, yeah, a higher dosage will give very little extra dispersion, but really significant secondary effects, so more retardation. In that case, then you should go for another type of admixture, and then I would say a super plasticizer. They are a lot used in a ready mix concrete companies. Now, if we look about the high range water reducing and super plasticizing admixture, so they are in dosage a bit higher than what we've seen for the plasticizing admixture, 0.2 to 2% on weight of the cement. And a positive about this admixture is they have minimal retardation, unless you really go to very high dosage. So which also means that, and you can see here, the application is also much wider, where you can apply them, where you really need a high workability. And there you can think of a structure where you are really dense reinforcement, and then your concrete really needs to go in everywhere. For the precast industry, they are highly used as water reducer because then you have a high early strength. And for the ready mix, the positive impact is that you can have extended workability. For then you can transport your concrete from your plant to a working place. This is also very positive if you work at elevated temperature. They have a lot of effects, so they are classified of the requirements. You have to assess them with two ways. First, you have to show with same water to cement ratio, which means that if you keep your same water to cement ratio, you will increase your consistency. So the first requirement is, okay, you have a reference concrete, and if you use the super plasticizing admixture, you should have at least an increase in slope from 120 millimeter compared to your reference. That would be in that case 30. And if you talk about the flows, then will be an increase of 160 millimeter compared to the reference, that will be 350. So you see that the effect is really big. But the super plasticizing is not increasing consistency only. You should also show some retention, or they also bring some retention of consistency. And this, the requirement is for superplast that 30 minutes after the addition, the consistency of your mix should be at least the same of your control mix. It could be higher, but cannot be lower. Then you also have some specification relating to the compressive strength. You have increased consistency, so same water to cement ratio, which means you have more water available for hydration. So in that case, it's also translated here by the requirement that the 28-day strength should be at least 90% of your control mix. So not 100%, because then virtually your water to cement ratio is a bit modified, but you still could have a good strength. And the same as before, the air content should not be more than 2% extra than your control mix. So if we look, I said that you should, we should look over a constant water to cement ratio. But then we should also look at if you have the same consistency, it means you bring some water reduction. And water reduction for super plasticizing admixture is 12% compared to a control mix, and this is really the low end because most of them you have 15 up to 30% of water reduction. So this is really a big reduction, so it means you can do much more with your mix design. Relating to your compressive strength, it means that after 1 day it should be more than 100%. 140% than the control mix, and at 28 days still the strength is higher than the control, so without your water reduction. And the air content should be also no more than 2% extra. In a super plasticizing admixture, we have 3 types. And the first one is a naphthalene formaldehyde condensate, and this brings 16 to 25% water reduction. You have to consider also if you use them in high dosage, they can bring some retardation. What is good about them, they have a good workability retention, and they're used a lot in a ready mix and site application. And if we look, the second type of super plasticizing admixture is a melamine, the same as a naphthalene, and they bring 16 to 25% water reduction. They have little of no retardation, which means they're also very effective at low temperature. If you use this type of admixture to consider, they will have a very quick loss of workability at high temperature. So depending of which application you target, temperature, is it low temperature or high temperature, this can also be a point of which admixture you need to use. The melamines are also less and less used, and that comes, and you can also see it in the name, formaldehyde. This is not so good for the health. So even it's in a really small amounts, it tends to be used less and less. And this comes also at the same time with the development of the polycarboxylate ether, the PCE. Nowadays, I think that more than 85% of the superplast are PCE based, and that is the expectation that in the future it will be more and more PCE based. You can see it's PCE already bring higher water reduction compared to what you have with your melamine of your naphthalene, 20 to 35% water reduction. And if you just look about the raw material, they are more expensive, but you can see with performance, they're also more powerful. So it's more expensive, but you will use lower dosage, better properties. So in the end, it won't bring extra cost in using them. They are used in a precast and a ready mix application. And I want to say a little bit more about PCEs. So this is a chemical formula on the left on a PCE, but often maybe you will see also in literature, they are schematically represented in what you can see on the right of the screen. And what you have, the first part, it's called the backbone. And then you have the carboxylate group that is called the anchor groups. They are negatively charged. And then you have side chain. So what is really nice about PCE, you have 3 different components. It's qua chemistry, you can act on every type and every part of the PCE, which means the property you can target for the PCE are really a lot. So this is my PCE. If you remember in the beginning, I mentioned that the cement particles, the aluminates, they are positively charged. And here you see that your PCE, your anchor group, is negatively charged. So what is going to happen? Your PCE will go to look for your C3A, and this is how it's going to adsorb. So now if I still take my 2 cement particles, so I have mine positively and negatively charged area, you have your PCE that is going to adsorb on the surface, and which means you will create some dispersion. Why are PCE so powerful compared to the other admixture? It's because the PCE have these side chains, and this is not the case in the other super plasticizers. So the naphthalene and melamine, they also adsorb on the surface of your particles. but then you will have electrostatic repulsion. So you will have repulsion dispersion, but it's not as strong that when you have the side chain, then you really have something physical. So you have there electrosteric repulsion, and it's more performing than only electrostatic. So this is the image that we had at the beginning. So you have your water that you trapped, but now if you have your PCE at the surface of your cement particles, then your water will be available for your workability. So I said a bit also, but there is so many ways you can work with your PCE. Yeah, you can play with the length and the chemical nature of your backbone. You can also play with a number of anchor group, which means with a charge density. So depending on the composition and the specification of your cement, how much aluminate are there of the charges, and you can target which type of PCE is best for this type of material. And then you can also play with the length and number of the side chains that you have. So you can have short chains, you can have high chains. So you can also imagine if you have short chains, the dispersion will be smaller than if you have a large chain. And then you can play, okay, how many chain I have? Do I have a lot of side chain, or do I have only a small amount of chain? And every variation that you bring in your structure can target properties you can have in your concrete. And at the time, what is a limiting parameter is more on the chemistry side. How can you synthesize them? Because you have infinite possibilities, but what you can do in a lab is not as infinite as on the paper. So the expectation is also, yeah, with the time in the future, we will have more and more different type also of PCEs. Are there questions? No?
I think I will ask a questions.
Yes.
So actually I have like two questions. The first, that actually beside that we use the super plasticizer, we know that by using this admixture we can improve the workability. However, actually are there any negative effects that can impact the concrete properties? And the second question is about how like we make sure that we select the right type of the super plasticizer to mitigate that there is no workability issue in our concrete mixture. Thank you.
Yes. So for the first one, yeah, there are. I show briefly that depending of which admixture you use or super plasticizer, depending of the temperature, it doesn't work the same. And for instance, for PCE, they tend also to entrain some air. But it's not, let's say, so the air content in your mix will be higher, and it's not something you want, because it is not, the distribution of your air content inside is not something you will control as you want with air entraining agents. But then we have another admixture for this, and this is a defoamer. So then you will compensate, let's say, the negative effect for your PCE with a defoamer, so that the air content or the negative effect of your PCE doesn't affect the properties of your concretes. And for, yeah, okay, how you can make sure how you choose the right PCE for your concrete. I will talk about it a bit in a second part. And if after the second part your question is still not answered, please ask again, and then we can discuss it.
Yeah, thank you.
Good. Are there any other questions? No? So I think we can have a short break. Anyway, I think there is time for. So I will suggest we do a small break, 10 minutes, and then we can continue with the rest of the admixture. Yeah?
Yeah, perfect. Okay, see you back in 10 minutes.
Okay, I think we are 10 minutes away now, or
I think so, so it's good to continue. Yeah.
Yeah. Okay, so I will continue. My screen is still shared, huh?
Yeah, it's still
Yeah.
there.
Okay, so I will continue. Okay. So I just presented the dispersing admixture, and now we'll go over the other families. And with a retarding admixture, and especially, so this is set retarding admixture, and that means that it is an admixture that will extend the time for the mix to change from the plastic to the hardened phase. So a delay should be a minimum 90 minutes, but should be no more than, 6 hours. And then you also have, let's say, admixtures that have main properties, and then you have secondary effects. So you can have a set retarding and also water reducing admixture. So it should anyway comply with the definition of set retarding, but at the same time, you also have some water reduction, and the same if you use a super plasticizer. So what are the requirements? Here the requirements are at equal consistency. And you see that the first requirement is dealing with the setting time, because we are retarding the setting time. So it means that no matter if you are using a set retarding admixture, a set retarding admixture plus plasticizing effect of super plasticizing effect, the delay of the setting, the initial setting, should be higher than your control plus the 90 minutes, and your final set should be less than the control mix plus the 360 minutes. So this is for the all categories. What applies also to the three categories is the air content in fresh concrete, and the same as a dispersing admixture, it should not be more than 2% compared to the control mix. Now what you see, you have a difference in a requirements in when it will deal with the compressive strength. If you have a set retarding admixture and as a standalone, it means that at 7 days, your compressive strength should be higher, 80% higher than your control mix. And at 28 days, 90% of your control mix. So it means that between also the 7 and the 28 days, you should have also an increase in strength. Now, if you use a retarding admixture that also have a plasticizing effect, it means you will have also an effect on your strength. And if you, in a case of plasticizing admixture, your strength at 28 days should be at least the same as your control mix. It can be higher, but cannot be lower. And if we look set retarding admixture, that is also a super plasticizer, it means you should have a positive effect of both 7 days and 28 days strength. So at 7 days, you should have at least the strength of your control mix. And at 28 days, you should have a higher strength, 115% higher than your control mix. It also goes in line with the water reduction. So if you have a standalone set retarding admixture, then you have no requirements relating to the water reduction. And then the same as a dispersing admixture, if it's a set retarder that is also plasticizing, then you should have at least 5% water reduction. And if you talk about set retarding admixtures that are also super plasticizing, you should have in addition the at least 12% water reduction. For the category, special category of set retarding super plasticizing admixture, you have an extra set of requirements, and this is for equal water to cement ratio. The first table I just presented was equal consistency. Now we have at equal water to cement ratio, which means that you have to have some extra requirements relating to the consistency, and that comes with a retention. With a set retarding, it means that 1 hour after addition of your admixture, your consistency should be at least the same as your control or higher. The air content, that is a constant one, no more than 2% by volume. And if you look about your compressive strength, then it should be more than 90% of your control mix at 28 days. What I haven't mentioned, I think, is when you have for the super plasticizing admixture, the requirement that you fulfill at same consistency or same water to cement ratio, it's not mandatory to use the same dosage. So if you have the properties at equal water to cement ratio, it means that you can also have an other dosage to have the other properties. Relating to the composition, what are retarding admixture made from? So it's largely on gluconates, sugar or phosphate. And this admixture also bring usually a bit of plasticizing effect. And if you have a retarding admixture with dispersing property, they are typically chemical composition the same as dispersing admixture, but they are usually combined with retarding, what we've seen as a sugar and gluconates. Rating to the dosage, it's also a low dosage, 0.2 to 0.6 on a weight on the cement. And if it's a multifunction, so a retarder plus dispersing properties, then the range dosage that is used is the same as the dispersing admixture. What you should be careful using retarding admixture, if you have like really an overdosage, that also happens sometimes on site, you should also take into account that the extension of the setting time is really delayed. And then it can run into days. So you have a significant delay on the setting time. How does it work? I will go back to this a slide of cement hydration. So, and here we've seen retarding admixture. They will extend the time for your mixture going for the plastic to the hardened phase. So it means it will increase your dormant period. In a dormant period, what do you have? You have a increase in concentration in your calcium and your silicate ions. Here it's like a gluconate, so when you will have gluconate in your solution, it will chelate, so it will trap your calcium, so which means that in solution, you will have less calcium available to reach your supersaturation. So it means this delay, you will have also a delay to nucleate and grow your hydrates. So you will have an extended dormant period, and that should be no more than 360 minutes compared to a normal hydration. So if you look about the applications, they are a lot used for ready mix and on-site concrete, and it's to help to have some workability retention and also to prevent the cold joints or a delay in pours. Now, if we move, like we say, retarding, now we will go to the opposite effect. If we look about accelerating admixture, so we have two types here of admixture. We have the set accelerating and we have the hardening accelerating. So I will first start with set accelerating admixture. So it has to do something with the setting. It will reduce the time to change from plastic to hardening. So which means and this part of the curve, when it will start, it will just shift to the lower time, but you see that the rate of your hardening, and it is between your initial and final set, the slope is the same. So it only influences the start of your initial sets. And then you can have an effect over your hardening rate, and this is hardening accelerating admixture. So it will increase the rate of development of your early strengths in your concretes. And this can be together with affecting or not your setting time. So you can have both. You can reduce your dormant period and at the same time also your hardening rate to increase your hardening rate. Or you have the same, let's say, dormant period. Your initial set will start at the same time, but the hardening will go much faster than your control mix. So what you will see here is that the slope will be steeper. So this is hardening accelerating admixture. If we look about the requirements, so these are requirements that are at equal consistency. So accelerating, the first requirements deals with setting time. And you can have set accelerating and you can also have accelerating admixtures that also have a plasticizing effect. So for both of them, at 20 degrees, the initial set should be no more than 30 minutes, and at 5 degrees should be less, that should be more than 60% of your control mix. So here you see that it is one of the admixture. You also have a requirement that is temperature related. So it gives you also an indication for which application it can be useful. If you look about the air content, nothing new here. You should not have more than 2% by volume compared to your control mix. And you also have some requirements relating to your strength, because it should accelerate, but sometimes can be at cost to your strength. You might think, oh, if it's faster, it would be better. But sometimes you have uncontrolled, how you say, strength development, and your microstructure can be less well defined. So for a set accelerating admixture at 28 days, the strength should be more than 80% of your control mix. And at 90 days should be higher than your 28 days. So it means that between 28 and 90 days, you should still have a strength development. If you use set accelerating admixture that also has a plasticizing effect, at 28 days, you should get at least the same strength as your control mix. And in that case, it means also that is an admixture that will show at least 5% of water reduction. In hardening accelerating admixture, so here it will increase the hardening rate. So here the first requirement is relating to the compressive strength, and at 20 degrees at 24 hours, so then you should get more than 120% than your control mix. And at 28 days, then you should have more than 90% of your control mix. And you also have here a requirement of your strength development at 5 degrees. And here is that at after 2 days, so 48 hours, your strength should be higher than 130% than your control mix. Air content, in any case, should be no more than 2% compared to your control mix. If we look about the dosage for the accelerating admixture, is typically 0.5 to 2% on the cement weight. And in the composition, usually you have one of the two effects. So it's either set accelerating or hardening accelerating, but rarely both of them. And they are largely based on inorganic material. Calcium chloride, maybe you have heard, it's like really one of the best accelerators. It gives both characteristics, so set and hardening accelerators, but a big negative effect for this one is alters the steel passivation due to the chloride that it has. So this is accelerating admixture that is not used, or you should not use it where you have reinforcements. Then you have chloride-free accelerators. So this can be salts of nitrate, nitrate, of other salts. And more recently, you have a seeding technology. And what is a seeding? For instance, where you have small particles that you can add in your mixture, it can act as nucleation points. So on the top of this picture, you can see a normal hydration. You have your cement particles. And at the surface, you have some cement hydration. And with time, you have the hydration product that grows from your cement particles. Now, what happens if you have what they call seeding technology? Then you have your cement particle and you will have your hydration product the same way. But where you have your seeds, and you can have a CSH seed, then it will be really like nucleation points, and which means that your hydration products can grow for much more area inside your system, and so your macrostructure will develop faster. This is a really nice technology, but it's also expensive relatively to the other accelerating admixtures. So for specific application, it's a really, let's say, an added value, but it's not something you will use for all application. If you look about mechanisms of the acceleration, so we can accelerate the formation of H-fringite or the nucleation of the hydrate. And if you look about the hardening accelerator, if you increase the rate of dissolution of your silicates, then you will increase the amount of CSH that you have at the early age, and CSH account for the compressive strength of your concrete. If you use also a high-range water reducer and super plasticizer, what happens is that you then you have water reduction. So the distance, what means water reduction is that your distance between two cement grain is smaller than when you have more water. So it means for the same amount of hydration product of CSH, the distance that needs to grow to link two particles is smaller, and then you have an accelerating effect and you have more strength. Accelerators are not that widely used if you look compared to the other admixture, and that comes also due to the cost effectiveness. They can be used at a low temperature because then you will need a really fast temperature development. But otherwise, if you are looking at normal temperature, then usually you will use a super plasticizer instead of accelerating admixture. And then you also have the positive effect on your workability and on your dispersion. Last category of admixture I will talk about today is the air entraining admixture. And these are admixtures that will control the quantity of air inside your mix, but it's not any type of air. And so the air bubbles need to be very small and really uniformly distributed. So you should have control over how is it distributed in your control mix. And so you have requirements. So it's okay, how much air you should have in your mix, but it's also specified what is the distance between two air bubbles. And this will give an indication of the freeze-thaw resistance. If we look about the dosage, it's also low dosage, 0.2 to 0.4%. What we really need to take into consideration when we talk about air entraining admixture, they are very powerful. And what does it mean? It's like you should really be careful with your dosage to be very accurate, because if you have a bit of overdosage, the impact of your distribution of your air can be really big. So if we look about the composition is surfactants. So surfactants have it's like chemicals that have two sides, one hydrophilic and one hydrophobic. So you can see it here. So what you see here on the picture, where you have the air, the surfactant, it stabilized the air. So instead, the air of going out of your cement mixture during mixing, it will stay here and stabilized, but it will also control the size of the air bubble. And usually is fatty acid salts. What is also largely used is vinyl resin. And then you can also have synthetic surfactants. If we look about the requirements, the first requirement of air entraining agents is, of course, the air content that you would bring inside your concrete mix. And it should be more than 2.5% compared to a control mix. But the total air content should be no more than 6% by volume. One aspect that is very important is the spacing factor. So the distance that would be between two air bubbles should be less than 0.2 millimeter. And I mentioned earlier that air content will have a direct impact over your strength. So here you will have more air, so you should expect lower strength, but if the strength at 28 days should be at least 75% than your control mix. If you look about the application, I think one of the most known is to increase the resistance to freeze-thaw action in the hardened concrete, but it can also be used to increase the cohesion and reduce the tendency to bleed in plastic concrete. It can also be used for compaction of low workability mixes and cohesion and handling property in blending mortars. So that was more a theoretical, let's say, part of the presentation. And to have a conclusion on that, the message is like, okay, chemical admixtures, they are added to the concrete, but very low amounts, but they have really can have very big effect on your concrete properties. On the one hand, they can modify your fresh properties. So what you have also with the workability, you can think about fluidity, slump retention, and also about your setting time. And it can also modify the properties in the hardened state of your concrete. So then also to have durability performances, you can increase the resistance to freeze-thaw. You can have a better strength development, corrosion inhibition. And of course, also if you use less clinker inside your concrete mix, you also increase not increase, but you reduce the carbon footprint. Are there questions for this part?
I have one question.
Yeah.
Hi. When we use acceleration, is it good for some situation that we are in a freezing situation?
In which, let's say, you should not have freezing. I think Michael also mentioned it. But then, yeah, it can help by low temperature to get the minimum strength to get before the concrete goes to freezing. So
it can be good for using acceleration, yeah?
Yeah, especially with low temperature, yes.
And for air in training, I'm not certain about it, but it is, I think, not very good, for instance, for durability properties. If it's, I don't know, we have a critical percentage for that due to the durability or not. For instance, for the
it can help the durability and depending on your application. But for instance, if you will have a construction that will be prone to a freeze-thaw, so you will have freeze and, with water, then you really need to have air entrainment, because then you will have these air bubbles that are, you control, let's say, the distance and how they are distributed inside the concrete. And only at that moment, when you have this characteristic, it will improve the resistance. So if you have a control mix, we'll have less air bubbles. It won't be resistant, so the water inside your mix will expand and provoke cracking. But with these small air bubbles, then it will have some buffer and resistance to this air cracking. But it's really specified how much and which distance should be between the air bubbles.
Okay, thank you.
Are there any other questions? No, so then I will continue. And with the last part, so development of admixture system, because then you say, okay, we have a toolbox with so many admixture, but how can we use these tools? And I mentioned, and in Cugla, we developed tailor-made admixture, and what are the, let's say, the inputs, and how is the philosophy behind. So I will start with a case that happened, unfortunately, often. So for instance, you have a case, and on the site, it was June, and they use, so they have a special workability, special admixture, and then they have a spread of 292 millimeter. Goes on, summer break, holidays, and then September, the same. They have cement, same mixed design, same admixture, and then suddenly the spread was much lower. So when you say, have you changed something in your mix design? Then we always get, no, I use the same one, 52.5 point air. And then it's always blamed on the admixture and say, yeah, your admixture doesn't work. Okay. Now, this is my question to you. What do you think could have happened that's to explain these two situations? Is really like the admixture, let's say during this time, yeah, degrade, doesn't work? Or is there something else that can happen that could explain this difference? So who wants to share his thoughts? Which other information would you need to, let's say, assess the situation?
Well, the superplasticizer might past the expiry date. That could be the problem, maybe.
And what would mean that it expires?
Yeah.
You mean it will degrade?
Yeah, to my knowledge, it does.
It can, because in that case not, but you also have, as you mentioned, an expiration date, because it's prone to microbial attack. You have in the environment, and then you have contamination, and then the, let's say, active part of the admixture can be degraded. But in that case was not the case. Okay, I will go to the next slide then. What we say is, okay, what we need to consider is when you have a cement, when you have a SEM1 52.5 air, doesn't mean that all cement have exactly the same composition. So if you have supplier 1 and you have supplier 2, both cement anyway will comply with the norm of the cements, and they will have the strength, and in a norm mortar, they will have the requirements. But if you look about the phase distribution, you see here like significant change inside the composition. So every time we say, okay, you can use one SEM1 52.5 air is not the same as from another supplier. So, and if you know what is the composition, then maybe you can think, okay, this might change the way your admixture works. So if you see this now, what do you think that could happen? And I will mention that the admixture was a PCE. So if you look about what is the interaction with your PCE and your cement, what will be the primaire interaction? So it will adsorb, but on which phase?
It has the interaction with the elite.
Not the first. The first interaction is with your C3A, so with your aluminate. So what do you see here if you have the aluminate?
There is an increase in C3A between SEM1, the first one, and the second one, and the increase is very high. And yeah, combining both the ferrites and C3A, I think it's higher in SEM1 too, the second
yes.
composition.
So this is something, and one of the first things we are looking at is C3A content and also your sulfates. And why is that? Is because I mentioned before, the first interaction that will take place between your PCE and your cement is with the C3A. It will adsorb on the surface area on your C3A. So if you have more C3A, then you can also see that the demand and the dosage on your superplast will be higher, because you will need to cover more spots than when you have less C3A. Also, if you remember, one of the first reactions that will take place is between your C3A and your sulfate. Then you will form Etrangite. And to make things even more easy, we don't have only one form of sulfite in cement, we have 3 forms of sulfite. You can have gypsum, basanite, or anhydrite. There are 3 forms of sulfate, but they won't have the same dissolution rate. So when it will be in contact with water, you will have some that will be in solution really fast, that can react really fast, and there will be some that will dissolve very slowly, so that will release the sulfate ions really slowly, so then you can react with your C3A in a more controlled way. So what is complex to assess the situation is that you don't have always one parameter that changes at a time. So you have at the same time some C3A, the distribution of your sulfate that is also changing. But what you can look at, if you have more aluminate, then you can say, okay, I will have an increase in my dosage of the superplast. If you look also of the type of sulfate that you have, your basanite will be the most reactive. So then we'll also increase your superplasticizer demand, because it will react really fast with your C3A, then it will form really fast Etrangite, and the Etrangite is also surface area to adsorb from your superplast. So suddenly the surface area where the superplast can react is much higher. So you will need a higher dosage to get the same dispersing effects. Another part that takes part, another parameter that also plays a role is your surface area. So if you look in this specific case between the first cement and the second one, you see that the specific surface area, and this was measured with a laser diffraction, you see that the second one is a bit finer than the first one. So it will be also more reactive, but will mean also that the surface area will be higher than the first cement. So usually also you see, yeah, if I have a finer cement, I will need more superplast because I need to cover more, more area. So with this in the background now, what do you expect when I will look into the workability of cement 1 and cement 2 if I use the same dosage of superplast?
The workability of SEM1-2 will be lesser in comparison to SEM1-1, the first one, because we have higher fineness. So we'll ideally need more plasticizer dosage.
Yes, that's exactly the case. And here to illustrate, so this is with the plastic viscosity that you see in function of the time. So a higher value means that you have something more viscous, so you have less workability. So, and it's what you see in, brown, it's like, this I made a mistake. The green one should be cement 2, and the second one should be cement 1, because it starts with a lower viscosity, and in the time with the hydration, you see that you have a loss of workability, but okay, this is expected. And you see that in the green one, that is a cement that has a higher amount of C3A and is also the finer. So you start already with a higher workability and you don't have much change because then it's already, let's say, you lost your workability almost immediately. So ideally, you will need, as you mentioned, higher dosage for the second cement than for the first one. So how can we a bit anticipate this type of situation? So in the lab, what we have a three-phase, research. We always start with material characterization. So what is the mineralogy with the XRD and what is the composition of my cement? But you can also think if you have different binder with your slag or also with your fly ash. What is the chemical composition with XRF, X-ray fluorescence? And of course, what is the fineness? Does it change in time or not? And when you have this information, then we are going to look about what is the interaction, how my superplast is going to interact with my binder or with my cement. And for this, we use two different methods. So the mini slump test. Then you can see the influence of the dosage and the workability. And what you have is that at the beginning, you will increase your dosage, but you won't have much influence over your workability until you reach a critical dosage. So you will have enough surface coverage of the cement to have a dispersing effect. And then you will see that a small difference in your dosage will have a bigger influence on your workability. So what you will have is something exponential. And then at a point, your admixture is all absorbed. So it won't help more with the workability. So it will flatten again, or then you will have segregation. So it's where you have your saturation dosage. So if you go above this dosage, it won't help anymore with the workability and the stability of your concrete. So between these 2 points, the critical and saturation dosage is where your dosage of your admixture is. And depending on the workability you want, you can choose your dosage. And to have an idea what is the PC reacts, then we use a TOC, and TOC stands for total organic carbon, and I'm going in a minute to say more about this technique. And once we have this, so we know if we have the right admixture for our system. And to answer maybe a question of Harry, I think, yeah, how will I make my first selection? Yeah, then it's really about a bit of know-how and experience. You know that, yeah, you should go with this type of admixture and you taste it. So it's not, you have no rule over there. You need to know a bit about the behavior of which admixture you have in-house. And then you go from paste on a mortar or a concrete, and then you can see how the full mix design behave. You can also look at the influence on the setting behavior. You can use ultrasonic sound transmission, non-destructive testing. And you can also see about the durability. AVR stands for air void analyzer. So it's where you can see in your concrete, in a fresh state, it's an equipment, you can measure how much air bubbles are there and how they are distributed. And this is really important when you work with air entraining agents, because you want to make sure that you have the right amount of the right size of the air bubbles and with the right spacing factor. And this equipment can give you this information. And then you can also do freezer resistance. So to come about the TOC, I mentioned in the first part of the presentation the adsorption of the PCE. So how much will, how you say, come into the surface of your cement. This is directly correlated over the dispersing effect of your PCE. And that, so we do, we have a method, so the TOC, to measure how much is adsorbed on your cement. And then that gives you an indication, are you in situation number 1, where what you put is nicely adsorbed on your cement particle, or in situation 2, where you have a cement particle, but you see that your admixture for some reason don't really attach to it, or then doesn't provide a dispersing effect. So in that sense, you will have more incompatibility with your cement. How we do this inside the lab? So we mix a cement paste in a traditional way with a Hobart mixer. Then you add your water and your admixture. And after 3 minutes mixing, then we use a centrifuge tube. And at that time, what you have is a cement paste, and inside your cement paste, you have your PCE. Then we do a centrifuge, and then you will separate your solid from your liquid phase. And what you will have in your solid phase is a PCE that is adsorbed. And what is in your pore solution? Yeah, it's free, so it means that it's a PCE that is not adsorbed on the surface of your cements. And this part we will measure with a TOC. So we know how much we have put initially. What we measure is how much is not reacted. So then we can just calculate how much has reacted. Is this clear? Yes?
Yeah.
Okay. So what we get from these measurements, here what is plotted on the horizontal axis, you see, okay, how much PCE I have put, so I have increased the dosage. And on the vertical axis, I measured, okay, how much has reacted. And ideally, if I have this dotted line, is everything I put has reacted, I should be somewhere on this line. Now I've tried a PCE, and this is the line what I get. So what I see is that theoretically, from the dotted line to the line I have a big difference. It means I try to schematize it on the right. You have my cement particles. I have my admixture, but only a small fraction is adsorbed of my cement particles, and the rest is in the pore solution. So it means that I have only a small fraction that is used for the dispersion of your cement particle. At that time, the other are not have any effect of function for the dispersion. So then I say, okay, I will try another PCE. I will try this one, and this is what you get. So you see here that the behavior between these two are different. So in the first case, and you see you have a small increase, and then you have a plateau. So the more you add, it won't adsorb more. So for some reason, because of the chemical structure of your PCE, it won't adsorb on your cement. And usually you say the more PCE, the more workability. But these measurements are interesting to know because, for instance, if in case of the blue PCE, you say, okay, 0.4, I still don't have enough workability. I want to go higher in dosage. Yeah, you should not do it because it won't help in a dispersing effect of your cement. And if you have too much PCE in your system, so overdosage of your admixture, then you will have segregation and not a homogeneous and stable system. But if you look about the red PCE, yeah, you see that you can increase until you get the plateau. So, and then you can determine when you are on the plateau, this is a saturation point. So this is the maximum that can adsorb from your PCE. So now if I look at this data a bit differently, I say, okay, I will take a dosage of 0.2 per weight on cement. And okay, what does it mean? It means that for my red PCE, I'm still on a dotted line. So everything I have put in the system is adsorbed as reactive. For the blue one, you see that you have a big difference between what has been reacted and your dotted line, what could have reacted, and you have only 1/3 that has reacted. So you have 2/3 that is still in solution. It's nice, but I still have no indication, okay, how does it translate to my workability in my system? Because in the end, it's what you want to know. So what happened? So here you have the two in parallel. On the left side, you see the red PCE, initially everything adsorbed. And the other one, you have a PCE that not a lot has adsorbed. So on the right, on the left case, it means, okay, everything I've put is on the surface of my cement, so there I get dispersion. On the right parts, you say, okay, only a small fraction, the rest is somewhere in a poor solution and it has not yet functionality. Now, if you look in the case of the red one, you have a fast adsorption because everything is immediately adsorbed, but then it also means that it's consumed really fast. Because with time, you have this hydration layer that grows. It will also grow if you have your superplast at a point. And at a point, your superplast will be trapped in your hydration layer. So it means that at that time, you have loss of functionality because the hydration layer from two cement particles will get into contact and you don't have PCE anymore in your solution. So this is where you see a loss of functionality. And what you will see in your mix, you have loss of workability. In the other case, I also have some hydration phase that grow on the surface of my cement. But in that case, what I have still in solution, I still have PCE, it is there. And then you say, okay, maybe that PCE has more affinity to adsorb on your H-rangite than to adsorb on your C3A. So when you have your hydration layer that grows, then you still have next to the hydration part, you still have some PCEs that can adsorb. And because it's absorbed on the surface of the hydration layer, then you still create dispersion. So in that case, you have increase of the functionality of your PCE, and it's how you create water retention. And what you can do, you can also combine both of them. So you can use the red one, then you will have initial workability. But because you also want to have retention of workability, you might put the blue one. And it means that when you will have hydration, you still have some PCEs that can adsorb on the hydration layer to still create this dispersion. And then you can really, let's say, target and fine-tune your properties of your admixture. So then you have long open time. So what I wanted to, the message here, what we can use with the TOC, and it's more in a preliminary files that you could use, is you can compare the adsorption behavior of your PC, and you can have also a database, and you know which function fast reactive, medium reactive, or for the open time. And you can also see what is the effect of the dosage. You can also see in time, will your admixture adsorb immediately? Maybe immediately won't do much, but you see that after 30 minutes, it will adsorb. And you can also check in that sense the effect with a time of addition. I haven't mentioned it yet, but if you put your admixture right away, or if you put your admixture apart immediately, and then you have a delayed addition, so a few seconds later, you add the rest of your admixture, you will get also different properties. And this has to do with the initial hydration and initial reaction that take place in the first minute of your mix. What is really interesting, you can also compare the effectiveness with the temperature, and will your PCE react the same with high temperature or low temperature? So then you can see if you do something in December, should you use the same admixture if you are doing concrete in July, for instance? And what is really interesting, you can also see with cement type. I just mentioned also if you have an OPC, and the same class of OPC still in composition can vary, and this can have effect of, let's say, the performance of your PCE. But if you have blended cement, and now they are more and more used, of when you have mineral addition, it means that the interaction of your admixture with your binder can be different. So this is something you can here assess. And the message is, yeah, it's not, let's say, one fits all, but it's really a tailor-made formulation for your binder, for your condition. And if something changes in composition, then you should look at, yeah, do I need to make an adjustment in my admixture, yes or no? So I will conclude with the same citation I start with. Again, ingredients of good concrete are very simple, but you can, with the same ingredient, make very bad concrete. And it's really knowing how this will interact that you can make good concrete. So know-how and understanding, and that also applies to admixture, because admixture has really so small amounts in a concrete, final concrete, that sometimes they say, oh, we just put a bit. But if you look, if you will have in your kitchen and to cook only with salt and pepper, you can do some things. But yeah, the range of tests you can create is not that big. So, and then when you have more spaces, then you can really do whatever you want. So that was for the presentation. Are there questions? Harry, did the second part answer your first question?
Yeah, I think it's very clear right now, and thank you so much. And maybe I just have like a doubt. My very last question, like because we typically use the super plasticizer. Actually, are there any difference if we use the super plasticizer in two scenarios? The first one, we dilute it with the water before we pour it down into the concrete mixture, or we just like make a few drops on the concrete mixture. Like, will it show like any difference on the like workability or not?
It will, and that comes with, yeah, how the first interaction that will take place. So when you will add it first, you dilute it in your water. So then you will have the first reaction and a dilution. So the phase that are then available to react with your admixture is different than if you just do some drop in your a dry mix. And it's the same also if you put everything at once, or if you mix a bit with your water, and then let's say that 30 seconds or 1 minute later, you will add another part of the water, and then with your admixture. Then you will see that for the workability, most of the time, but not always, you have increased workability. Because then you have, let's say, your really first initial reaction that take place between your C3A and your sulfate. So you have some heterogate that is formed, and that can trap also sometimes your superplast. And then your superplast will directly adsorb on your heterogate. So, and usually in that case, you have more slump retention.
Okay, yeah, thank you so much.
Are there other questions?
Yeah. First of all, thank you for the presentation. I want to ask about if there are any possible scenarios or environmental conditions where the usage of PC-based superplasticizer is not possible?
Not as far as I know, but let's say I will ask, and I will come back to you with a more a clear answer. I will ask my colleague that is this I didn't mention, but okay, at Cugla, I'm responsible for the Mortar parts of the production and R&D, and my colleague do everything with the admixture and the PCE. So I will ask him, and
Okay.
And then I will come back to you with an answer in that case.
Okay, thank you.
Are there other questions? No. So I think, yeah, there was one part for discussion, but I think we are now, the time is almost up. But to take into consideration and also what you can take for your case study for tomorrow, you have your healing technology and your self-healing agent. Look at, does it affect my concrete property? And if yes, is it a property that you would not like to see? Which type of admixture would you like to use to compensate, let's say, this negative effect on your concrete? And if it's, let's say, a property of an effect that I haven't mentioned yet today, you say, okay, this is the admixture of the future. This is the admixture that we will need to be able to add this healing technology inside the concrete. And you can also see it in another way around, and that is also in the line mentioned by Virginie Wiktor yesterday. You say, okay, I have a healing agent. I see that it affects the fresh properties of my concrete and maybe also the hardened properties. Does it affect it in the same way of a current admixture? And so that your healing agent will be an admixture that's so as defined in the norm, and then an additional added value will be also an healing properties. And you see that up to now in the norm, you don't have admixtures that also have these healing properties. So then you also have, let's say, have a gap, and you can yeah, have a window to have a self-healing concrete in that way. Good. So I think.
See, Virginie, there are also two questions in the Q&A.
Ah, yeah. Okay. Yeah, you haven't seen
outside. I think they are asked now. The first one is: did Romans really use blood as agent?
Well, I was not there to check, but this is what I found in literature. So.
Okay.
And they wrote, they ask because it was like air and training agent, right?
Yes.
And so they ask any ideas how it could work.
This not, but I know if you look also. No, it was with hemoglobin. But hemoglobin is also used to transport in the blood the oxygen, and so then you can say maybe it helps to trap the air, and then when you will put it then in your concrete, you will have more air. But the exact mechanisms not. But maybe do I have it here as a recommended lecture? But I will put it in a file for the MS. So this is a book. It's really interesting and. About admixture, and think there you find also how they used the blood initially, but you can find more details information and also more in depth over this.
Okay. There is a second question. Could the self-healing bacteria modify or reduce the performance of the admixtures? Will they fight with each other?
Well, as far as I know, is that the bacteria are in a dormant state, so the bacteria itself not. Now the food for the bacteria that I know that can have an effect also on the fresh properties. You should also see that yeah, PCEs are also used in blends, so they can also be used with other type of admixture. So it needs to be tested, but I think it can be used together.
Okay. Yeah.
And
Other
especially,
questions?
yeah, sorry.
in here? No more questions from our ESRs? No, don't seem so. So thank you very much, Virginie, for a very interesting lecture. I think we had 4 very nice contributions today, looking at concrete from 4 different angles. And I think that really helps you to design your concrete mix. At least you can have a lot of ideas and tips how to do that and how to increase the performance of your material, and also how to include self-healing agents, but that yes, your own development, so that but you can look at all the talks from today, how that can help you. So that brings us to the end of day 4 already. 1 more day to go. Then we go to Concrefy, to another company in our Smart Things project. And they will show what they are doing on the research side and how they do also European projects. So they will tell about that. And then, of course, you have to work on your assignment. The good thing is that we start tomorrow at 10 o'clock, so you have in the morning already time to work on it. And also in the afternoon, because we start then after the visit to Concrefy, the virtual visit, we will start at 3:30 with the presentations. So make sure that you have done the work, have a presentation ready, and you have to decide yourself who is going to present. You can, because you are in groups of 5 people, you can all present a little bit, or you can assign 1 person to do it. That's up to you. At least I look forward to the outcome of your projects. What are you going to do with this? With these swimming pools, how long will they still live? And after that, we will also have some fun. Because Mana and I are working on the pop quiz in the meantime. So, well, it's starting to look good. So, looking forward to that. And of course, we want to see what you prepare for dinner. So, we'll see that tomorrow. So, Virginie, thank you again for today. And see you also back tomorrow, maybe?
Yes.
Yeah, okay.
Thanks.
Goodbye. Have a nice evening, everyone.
Bye-bye.
Bye.
Bye-bye. Bye-bye. Thank you.